Hello, guys. Alright, let's talk about space. And I don't mean the, oh, the stars are pretty kind of talk. I mean the what the heck is going on out there kind of talk. Because the more you look at the universe, really look at it, the more you realize that reality is way, way stranger than anything we could make up. We're talking about places where time slows down. Objects so dense that a single teaspoon of them would weigh more than a mountain. Signals from deep space that we still can't explain. And a universe that is, right now, as you listen to this, flying apart in every direction, faster and faster, toward an end that scientists are still arguing about. So buckle up. We're going on a trip. No rocket needed. The universe is stranger than you think. The size of the universe, and why your brain will crash trying to understand it. Let's start with a number, 93 billion. That's how many light years across the observable universe is. Not the whole universe, just the part we can see. The part where light has had enough time to travel and reach us since the Big Bang. Now, a light year is the distance light travels in 1 year. And light moves at about 300,000 kilometers per second. So in 1 year, light covers roughly 9.5 trillion kilometers. Multiply that by 93 billion. I'll wait. Yeah. It doesn't fit in your head. That's okay. It doesn't fit in anyone's head. Here's another way to think about it. If you shrunk the sun down to the size of a white blood cell, something you can only see under a microscope, the Milky Way galaxy would be the size of the continental United States. And the observable universe? It would be larger than the entire planet Earth. And here's the part that really gets me. That's just the observable universe. The actual universe could be infinitely larger. We genuinely don't know. The universe might go on forever, filled with galaxies and stars and maybe even other versions of everything we know, stretching out in every direction with no edge, no wall, no "you are here" sign. We are, in the most literal sense possible, a tiny speck of dust on a tiny speck of dust, floating in something so vast it has no name worthy of it. And somehow, that tiny speck figured out how to look up and ask questions. Which, honestly, kind of impressive. The universe is expanding, and it's speeding up. Here's something that sounds wrong but is absolutely true. Every galaxy in the universe is moving away from every other galaxy. Right now, as you sit there listening to this, it's not like they're moving through space towards some faraway destination. Space itself is stretching. The fabric of reality is expanding, carrying everything with it. Edwin Hubble figured this out in the 1920s when he noticed that the light from distant galaxies was shifted toward the red end of the spectrum, what astronomers call redshift. That's the light equivalent of the Doppler effect, the same reason a police siren sounds higher as it approaches you and lower as it drives away. If a galaxy is moving away from you, its light gets stretched, shifted toward red. And the farther away a galaxy is, the faster it's moving away from us. Which means at some point, at distances far enough, galaxies are moving away from us faster than the speed of light. Not because they're traveling faster than light, but because space itself is expanding that fast. Those galaxies are already beyond our reach, forever. We will never see them, never interact with them. They're gone. Now, you'd think that after the Big Bang, this expansion would be slowing down. Gravity should be pulling everything back together, right? Like throwing a ball in the air. It goes up, it slows down, it comes back. But in 1998, 2 teams of astronomers made a discovery so shocking it won the Nobel Prize. The expansion of the universe isn't slowing down. It's speeding up. Something is pushing the universe apart. We call it dark energy. And here's the embarrassing part, we have absolutely no idea what it is. We just know it exists because the math doesn't work without it. Dark energy makes up about 68% of the total energy content of the universe, and we can't see it, touch it, or explain it. The universe is mostly made of something we don't understand. Cool. What was there before the Big Bang? Okay, here's where things get philosophically uncomfortable. The Big Bang happened approximately 13.8 billion years ago. In a fraction of a second, everything, all of space, all of time, all of matter and energy, exploded into existence from an unimaginably hot, dense point. And the natural question is, what was there before that? The unsatisfying but honest answer is, the question might not make sense. Here's why. Time, as we understand it, is part of the universe. It was created in the Big Bang along with space and everything else. Asking what happened before the Big Bang is like asking what's south of the South Pole. The concept doesn't apply. But of course, that hasn't stopped physicists from speculating. And the ideas are wild. Some physicists like Stephen Hawking and Jim Hartle propose that the universe has no boundary in time, that if you could travel back through the beginning, time would gradually become another dimension of space, and there would simply be no edge. No moment of creation, just a smooth curve. Other theories suggest that our Big Bang was the result of two membranes of reality, called brains, colliding in a higher dimensional space, like two soap bubbles touching. There's also the idea of eternal inflation, the notion that our universe is just one bubble in a vast, forever inflating multiverse, where new universes are constantly being born from quantum fluctuations in the space between them. And then there's the simplest, most maddening possibility. Maybe the laws of physics as we know them simply break down at the Big Bang. Maybe the universe didn't come from anything. Maybe it just started. We don't know. And that's not a failure, that's the frontier. Black holes, the monsters of the cosmos. What is a black hole, really? Pop quiz. What do you picture when you hear black hole? If you're imagining some kind of giant cosmic vacuum cleaner, sucking up everything in sight, that's a myth. Black holes don't suck. They're not vacuums. They're gravity wells, and they follow the same rules as every other massive object in the universe. Here's what a black hole actually is. It's a region of space where gravity is so strong that nothing, not even light, can escape once it crosses a certain boundary called the event horizon. How does something get that gravitational pull? Massachusetts. A lot of it packed into a very small space. When a massive star, something at least about 20 times more massive than our sun, reaches the end of its life and explodes in a supernova, its core can collapse under its own gravity into a point of infinite density called a singularity. The gravity around that point becomes so intense that it warps space and time in ways that feel almost supernatural. And the event horizon, that's the point of no return. Cross it and you're not coming back. Not because something is pulling you in, but because beyond that boundary, every possible path through space and time leads inward. There's no direction you can move that takes you away from the center. The concept of away stops existing. That's a black hole. Now, and this is the part where it gets really weird, black holes aren't all the same size. There are stellar black holes, which are maybe 5 to 20 times the mass of the sun. There are intermediate black holes. And then there are supermassive black holes, the monsters at the centers of galaxies, with masses millions or billions of times greater than the sun. The black hole at the center of the Milky Way is called Sagittarius A*, and it has the mass of about 4 million suns. And yet, in cosmic terms, that's almost small. The black hole at the center of the galaxy M87, the one we actually photographed in 2019, has a mass of about 6.5 billion suns. That image of the M87 black hole, by the way, the glowing orange ring around a dark shadow, that wasn't taken with a single telescope. It required a planet-sized array of radio telescopes all working together, turning the entire Earth into one giant instrument, just to get enough resolution to capture something 55 million light-years away. Worth it. What happens if you fall into a black hole? I'm so glad you asked, because the answer depends entirely on whether you're watching from the outside or experiencing it yourself. And those two answers are completely different, and both are completely true at the same time. Let's start with an outside observer. Imagine you're watching a friend fall into a black hole. A brave friend. From your perspective, as they approach the event horizon, something strange happens. Because gravity warps time, and the closer you are to a massive object, the slower time flows for you. Your friend's movements start to slow down. They get slower and slower and slower. Their image gets redder and dimmer as their light gets stretched. And eventually, they appear to freeze just at the edge of the event horizon, never actually crossing it, fading away into darkness over an incredibly long time. From your perspective, they never fell in. Now switch perspectives. From your friend's point of view, they cross the event horizon without even necessarily noticing. There's no wall, no alarm, no sign saying, point of no return. They just keep falling. But here's where it gets grim. As they fall toward the singularity, they experience something physicists delightfully call spaghettification. The gravity gradient becomes so extreme that the tidal forces, the difference in gravitational pull between your head and your feet become large enough to stretch you out like spaghetti. Long, thin, stretchy human spaghetti. For a stellar mass black hole, this happens before you even cross the event horizon. You'd be torn apart instantly. But for a supermassive black hole, the event horizon is so far from the singularity that you could cross it and travel for hours before spaghettification gets you. You'd have plenty of time to contemplate your situation. Now here's the twist that nobody agrees on. What happens to the information about you, the quantum information that makes up every particle of your body, when you fall in? According to Stephen Hawking's work, black holes actually slowly evaporate over incredibly long time periods through a process called Hawking radiation. Quantum effects near the event horizon cause the black hole to slowly leak energy and shrink. Eventually, it evaporates entirely. But if it evaporates, where does the information about everything it ever swallowed go? Does it vanish? Physics says information can't be destroyed. This is called the black hole information paradox, and it's one of the biggest unsolved problems in theoretical physics. We genuinely do not know. The black hole in the center of our galaxy. Right now, 26,000 light-years from Earth, at the very center of the Milky Way, there is a black hole 4 million times more massive than the Sun. Sitting there, quietly, waiting. Okay, it's not really waiting, black holes don't do anything on their own. But Sagittarius A* is real, and it's ours, and astronomers have been studying it for decades. For a long time, we only knew it was there because of how stars near the galactic center move. These stars, given names like S2 and S62, orbit around an invisible point at incredible speeds. S2 completes a full orbit around Sagittarius A* in about 16 years. For comparison, Earth takes 230 million years to orbit the Milky Way once. S2 is moving fast. By tracking those orbits over years and decades, astronomers could calculate the mass and size of whatever was at the center. And the only thing that could be that massive and that compact: a supermassive black hole. Then, in 2022, the Event Horizon Telescope collaboration, the same team that photographed M87, released the first actual image of Sagittarius A star. It's blurry, it's orange, it's a glowing ring of gas around a dark shadow, and it is one of the most remarkable things humanity has ever produced. We photographed the black hole at the center of our own galaxy. Let that sink in. And by the way, Sagittarius A* is surprisingly quiet right now. Supermassive black holes in other galaxies are actively feeding, surrounded by blazing disks of superheated gas called accretion disks, blasting jets of energy across the cosmos. Those are called active galactic nuclei, or quasars at their most extreme. Our black hole is just sitting there, not eating much, which is fortunate, because an active Sagittarius A* would make life in the Milky Way significantly more difficult. The solar system is a bizarre place, the strangest planets and their wildest phenomena. Let's take a tour of our cosmic neighborhood, because our solar system is full of places that sound completely made up. Venus, let's start next door. Venus is often called Earth's twin because it's similar in size and composition. But that's where the similarity ends. Venus has a surface temperature of around 465 degrees Celsius, hot enough to melt lead. Its atmosphere is thick with carbon dioxide and clouds of sulfuric acid. The atmospheric pressure at its surface is 92 times that of Earth's, equivalent to being 900 meters underwater. Oh, and here's a fun one. Venus rotates so slowly, and in the opposite direction to most planets, that a day on Venus is longer than a year on Venus. The sun rises in the west and sets in the east, but you'd only see it about twice a year if you were standing there, which you absolutely could not do. Jupiter, the king of the planets. This gas giant is so massive that it could fit more than 1,300 Earths inside it. Its famous Great Red Spot is a storm that has been raging for at least 350 years, and it's shrinking. When it was first observed in detail, it was big enough to swallow 3 Earths. Now it's only about 1.3 Earths wide. Astronomers are watching closely to see if it'll disappear entirely. Jupiter also has the most intense magnetic field of any planet in the solar system, 20,000 times stronger than Earth's. If you could see it with the naked eye from Earth, it would appear larger than the full moon. Saturn, you know about the rings, but do you know what they are? They're not solid. They're billions of individual pieces of ice and rock, ranging from tiny grains to chunks the size of houses, all orbiting Saturn in a flat disk. And they're surprisingly thin. The rings span up to 282,000 kilometers wide, but are often less than a kilometer thick. Proportionally, they're thinner than a sheet of paper. Saturn is also the least dense planet in the solar system. It's so light that if you could find a bathtub big enough, Saturn would float. Uranus rotates on its side. Its axial tilt is 98 degrees, meaning it essentially rolls around the sun like a bowling ball. Its north pole spends 42 years in complete darkness, followed by 42 years of continuous sunlight. A season there lasts decades. Also, and I cannot stress this enough, Uranus smells terrible. Scientists confirmed that its upper atmosphere contains hydrogen sulfide, the gas that gives rotten eggs their distinctive odor. Walking on Uranus, if you could, would be like walking in a cosmic gas leak. Moons that might have life: Europa, Titan, Enceladus. Here's something that might change how you think about life in the solar system. The most exciting places to search for life might not be planets at all. They're moons. Europa, Jupiter's moon Europa, is covered in a thick shell of ice. But beneath that ice, there's a liquid water ocean, probably larger than all of Earth's oceans combined. We know this because the surface of Europa is covered in cracks and ridges, evidence of a dynamic, moving ice shell being pulled and stretched by Jupiter's enormous gravity. That gravitational flexing generates heat, keeping the water below liquid. Where there's liquid water and a heat source, life as we know it can thrive. We've found life in the deep ocean vents on Earth, complete ecosystems in total darkness, powered not by sunlight but by chemical energy. Could the same thing be happening on Europa? We don't know yet, but NASA's Europa Clipper mission, launched in 2024, is on its way to find out. Enceladus, Saturn's small moon Enceladus, is one of the most exciting places in the solar system. It's a tiny, ice-covered world, only about 500 kilometers across, but it has geysers. Actual geysers erupting through its south pole, shooting plumes of water vapor and ice into space at 1,400 kilometers per hour. And when the Cassini spacecraft flew through those plumes, it found something extraordinary: water, salt, organic molecules, and, crucially, molecular hydrogen. That hydrogen is almost certainly produced by hydrothermal vents on the ocean floor, where hot water reacts with rock. On Earth, those exact conditions support entire communities of life. The ingredients for life are erupting into space from Enceladus. Right now, we could, in theory, fly through those plumes and sample them for signs of biology without even landing. Titan, Saturn's largest moon, Titan, is a world of orange haze and hydrocarbon seas. It's the only moon in the solar system with a thick atmosphere, and that atmosphere is primarily nitrogen, like Earth's. But Titan is far too cold for liquid water. Instead, it has lakes, rivers, and even rain, but all made of liquid methane and ethane. Could life exist in methane lakes? On Earth, no, our biology is built on water. But some scientists have proposed that life could potentially arise based on different solvents, in completely different biochemistry. We have no idea if it's possible. But Titan is the ultimate test case. NASA's Dragonfly mission is scheduled to fly a rotorcraft drone on Titan in the 2030s. A drone, on another moon, flying through orange skies over methane lakes. We live in an extraordinary time. The asteroid belt, and what it's not. Pop culture has given us a very specific image of the asteroid belt. A dense, chaotic field of rocks that spaceships have to weave through at high speed. Explosions everywhere, drama at every turn. I hate to break it to you, but real asteroid belts are profoundly boring to fly through. The asteroid belt between Mars and Jupiter is actually remarkably empty. If you were flying a spacecraft through it, which we've done many times, the average distance between objects is about 970,000 kilometers. You'd have to go out of your way to hit anything. The total mass of everything in the asteroid belt is less than 4% of the mass of the moon. It's not the remains of a destroyed planet, despite what movies suggest. It's material that never became a planet, because Jupiter's gravitational influence kept stirring things up and preventing accretion. But don't be too bored. The asteroid belt does have some genuinely fascinating objects. Ceres, the largest, is big enough that it's classified as a dwarf planet. And NASA's Dawn mission revealed it has strange bright spots in some of its craters, reflective deposits of salt left behind by ancient water that seeped up from a subsurface ocean and evaporated. Ceres might have once been, or still be, geologically active. And then there are near-Earth asteroids, which are a whole other story. Some of them do cross Earth's orbit, and some of them have a non-zero chance of hitting us in the future. Apophis, a 370-meter-wide asteroid, will pass uncomfortably close to Earth in 2029, close enough to be visible to the naked eye, passing below the orbits of some of our satellites. That's why we have planetary defense missions now, including NASA's DART mission, which in 2022 successfully changed the orbit of an asteroid by crashing a spacecraft into it. We moved an asteroid, on purpose, with a rocket. Humanity, 1. Space rock, 0. Stars, from birth to apocalypse. How a star is born and how it dies. A star begins as a nebula, a vast cold cloud of hydrogen gas and dust, drifting through space for millions of years. Then something disturbs it. Maybe the shockwave from a nearby supernova. Maybe a gravitational interaction with another cloud. Whatever the trigger, parts of the cloud start to collapse under their own gravity. As the gas falls inward, it heats up. The cloud fragments, each piece collapsing faster and faster, getting hotter and denser. At the center, a protostar forms, a hot, dense object that's not quite a star yet. It's pulling in material from the surrounding disk of gas and dust, growing larger. Then, when the core gets hot enough, about 10 million degrees Celsius, something magical happens. Nuclear fusion ignites. Hydrogen atoms fuse together to form helium, releasing an enormous amount of energy. And that energy pushes back against gravity, balancing the collapse. The protostar becomes a star. Our sun has been doing this for about 4.6 billion years. It's middle-aged, and it'll keep doing it for another 5 billion years or so, maintaining that balance between gravity and fusion. But eventually, the hydrogen in the core runs out. When that happens, the core starts to collapse again, heating up further while the outer layers expand outward. The sun will swell into a red giant, potentially large enough to engulf Mercury, Venus, and possibly Earth. Our oceans will boil away. The surface will be scorched bare. Don't panic, this is 5 billion years away. You have time to finish listening to this. After the red giant phase, a star like the sun sheds its outer layers in a beautiful expanding shell called a planetary nebula. Nothing to do with planets, just a historical naming mistake. The name stuck. What's left at the center is a white dwarf, a tiny, incredibly dense, slowly cooling ember of what was once a star. A white dwarf is about the size of Earth but contains the mass of the sun. A teaspoon of white dwarf material would weigh about 15 tons. It's not undergoing fusion anymore. It's just slowly radiating away stored heat into the darkness of space, cooling over billions and billions of years, until eventually it becomes a cold, dark object called a black dwarf. Here's a fun fact. No black dwarfs exist yet. The universe isn't old enough. It would take longer than the current age of the universe for a white dwarf to cool down that much. All the white dwarfs that have ever existed are still glowing. Supernovae, the biggest explosions in the universe. For a massive star much bigger than our sun, the ending is not a gentle exhale. It's a catastrophe. When a massive star runs out of fuel, the core collapses in less than a second. Less than a second. What was a volume several times larger than the sun collapses to a sphere about 20 kilometers wide. The infalling outer layers hit that incredibly dense core and bounce outward in a shockwave of unimaginable power. This is a supernova. In those few seconds, the supernova releases more energy than our sun will emit in its entire 10 billion year lifetime. For a brief period, a single exploding star can outshine an entire galaxy of 200 billion stars. Supernovae are important for reasons beyond their spectacle. All the heavy elements in the universe, the iron in your blood, the calcium in your bones, the gold in jewelry, the oxygen you're breathing right now, were forged either in the cores of stars or in supernova explosions. The Big Bang only produced hydrogen and helium. Everything else came from stars. You are, in a very literal and scientifically accurate sense, made of star stuff. The most famous supernova visible in historical records is SN 1006, which appeared in the year 1006 AD. Astronomers across China, Egypt, Iraq, Japan, and Europe recorded a star so bright it cast shadows at night. It remained visible for about 3 years. We can still see the expanding shell of gas from that explosion today, 1,000 years later, spread across 60 light-years of space. In 1987, a supernova occurred in the Large Magellanic Cloud, a small galaxy near the Milky Way. It was the closest supernova to Earth in nearly 400 years, and it was detected not just with light, but with neutrinos, ghostly subatomic particles that barely interact with anything. Detectors underground around the world registered a burst of neutrinos 3 hours before the visible explosion was seen. That 3-hour lead time was the neutrinos escaping the collapsing core before the explosion even broke through the surface of the star. That's how we know what's happening inside a supernova. We caught the neutrinos fleeing first. Neutron stars and pulsars, the most extreme objects that still exist. After a supernova, if the star wasn't quite massive enough to form a black hole, what's left is a neutron star. Neutron stars are what happens when you take about 1 to 2 times the mass of the Sun and crush it into a sphere about 20 kilometers across. The density is so extreme that electrons and protons are forced together to become neutrons, hence the name. The neutrons are packed so tightly that they're essentially touching. A teaspoon of neutron star material would weigh about 4 billion tons. On Earth, if you could somehow bring a sugar cube-sized piece of neutron star to your kitchen table, it would immediately fall through the table, through the floor, through the Earth's crust, through the mantle, through the core, and out the other side. It wouldn't stop. Well, actually it would eventually settle at the center of the Earth, where its gravity would start pulling everything inward. Please don't bring neutron star material to your kitchen. Now, pulsars are a type of neutron star that's spinning incredibly fast and emitting beams of radio waves from its magnetic poles. Because these beams sweep around like a lighthouse, from our perspective on Earth, we detect regular pulses of radio waves, hence the name. The fastest pulsars spin hundreds of times per second. Some complete more than 700 rotations per second. That's a star with the mass of the Sun, fitting in a city, spinning 700 times a second. If a pulsar were the size of a basketball, its surface would be moving at a significant fraction of the speed of light. And neutron stars can collide. In 2017, we detected gravitational waves, actual ripples in the fabric of spacetime, from 2 neutron stars spiraling together and merging in a cataclysmic explosion called a kilonova. When astronomers pointed telescopes at the source, they watched as heavy elements, gold, platinum, uranium, were synthesized in real time and flung into space. That was the first time we directly observed where gold comes from. It comes from colliding neutron stars. Every piece of gold on Earth was forged in an ancient collision of 2 dead stellar cores, billions of years ago, before our solar system formed. Your wedding ring is debris from a stellar apocalypse. Are we alone? The question of extraterrestrial life. The Fermi paradox. If there's so much life out there, where's everybody? In 1950, physicist Enrico Fermi was having lunch with colleagues at Los Alamos, and the conversation turned to the possibility of extraterrestrial civilizations. And Fermi, in his characteristically direct way, asked a question that has haunted scientists ever since. Where is everybody? Think about it. The Milky Way has about 200 to 400 billion stars. A large fraction of those have planets. A fraction of those planets are in the habitable zone. Life on Earth arose relatively quickly after conditions became favorable. Evolution, given enough time, seems to produce intelligence. It happened here. By the most conservative estimates, there should be thousands, maybe millions of civilizations in our galaxy alone. And even if they never traveled faster than 1% of the speed of light, a civilization that had a million-year head start on us could have colonized the entire Milky Way in a few 100 million years. But we look at the sky and we see nothing. No signals. No visitors. No evidence of anyone rearranging stars or megastructures or anything that screams, "We were here." This is the Fermi paradox, and it has a disturbing number of possible solutions. Maybe life is just absurdly rare. so rare that we might be the only intelligent life in the entire observable universe. Maybe the origin of life, despite its apparent simplicity, requires a chain of events so improbable that it only happened once. Maybe intelligence arises fairly often, but complex life gets wiped out before it can become spacefaring, by asteroid impacts, supernovae, climate change, or self-inflicted catastrophes. This is sometimes called the Great Filter, and the question is the filter behind us or ahead of us? Maybe civilizations do reach technological maturity, but then go quiet, either destroying themselves, losing interest in expansion, or deliberately hiding for reasons we can't fathom. Or maybe, and this one is unsettling, we're being observed right now, and they've decided not to make contact. The zoo hypothesis: Earth is a nature reserve, and we're the animals. We don't know. Any of these could be right. All of them could be partially right. The silence is real, and the silence is deafening. Mysterious signals from space. Wow! Fast radio bursts, and Oumuamua. Sometimes the universe sends us something we don't understand, and we have to sit with the mystery. The wow! Signal. On August 15, 1977, astronomer Jerry Emin was sifting through data from the Big Ear radio telescope at Ohio State University, searching for signs of extraterrestrial intelligence. And he found something that made him grab a red pen and write "wow" in the margin of the computer printout. What he found was a radio signal that lasted 72 seconds, the maximum time the telescope could observe a single point in the sky. It was in exactly the right frequency range that scientists predicted an alien civilization might use for interstellar communication. It was incredibly strong. It came from the direction of the constellation Sagittarius, and it was never detected again. Dozens of attempts to find it have failed. We have no verified explanation for what caused it. Could it have been a natural astrophysical source? Possibly. Could it have been a one-time transmission from somewhere out there? We genuinely cannot rule it out. The wow signal remains the most intriguing unexplained signal in the history of SETI, the search for extraterrestrial intelligence. Fast radio bursts, these are another mystery. Fast radio bursts, or FRBs, are intense pulses of radio energy that last just milliseconds but release more energy than the sun emits in thousands of years. They come from billions of light years away, and they were only discovered in 2007. Some FRBs repeat. The same source fires again and again at seemingly random intervals. We now think most of them are caused by magnetars, a type of neutron star with a ridiculously powerful magnetic field, having some kind of catastrophic surface event. But we're not 100% certain, and the repeating ones are still not fully understood. Oumuamua, in 2017, astronomers detected the first known interstellar object to pass through our solar system. They named it Oumuamua, Hawaiian for scout or messenger. It was strange, very strange. Its shape was unusual. Estimates suggested it was extremely elongated, like a cigar or a pancake. It was tumbling, and most bizarrely, as it left the solar system, it accelerated slightly more than gravity alone could explain. It was being pushed by something. The most straightforward explanation is outgassing. Comets do this when sunlight vaporizes their ice, creating a small thrust. But astronomers couldn't detect any sign of outgassing from Oumuamua. Harvard astronomer Avi Loeb controversially suggested that Oumuamua might be a piece of alien technology, possibly a light sail from an extraterrestrial civilization. Most scientists are skeptical, but the explanation that satisfies everyone hasn't been found yet. Oumuamua is long gone now, heading out of the solar system. We'll never catch it. Whatever it was, it passed through our neighborhood in cosmic silence and left us with questions. What does science actually say about the search for life? Let's bring this back down to Earth, figuratively. The scientific consensus, as of now, is that we haven't found definitive evidence of extraterrestrial life. Not intelligent life, not microbial life, not even convincing biosignatures. But the search has never been more promising. The James Webb Space Telescope, launched in 2021, is capable of analyzing the atmospheres of exoplanets, planets orbiting other stars, as they pass in front of their host star. The starlight filtered through a planet's atmosphere carries a chemical fingerprint. And we're looking for things like oxygen, methane, water vapor, or other molecules that might indicate biological processes. In 2023, JWST detected a molecule called dimethyl sulfide in the atmosphere of a planet called K2-18b, a molecule that, on Earth, is only produced by marine organisms. This was not a confirmation of life. There could be non-biological explanations, but it was the kind of signal that gets scientists very, very interested. Meanwhile, Mars exploration continues. The Perseverance rover is collecting and caching samples from Jezero Crater, an ancient lake bed, for eventual return to Earth. If there was ever life on Mars, those samples might tell us. A Mars sample return mission is being planned for the early 2030s. And beyond our solar system, the planet catalog is exploding. We know of over 5,000 confirmed exoplanets, and the count grows regularly. Some are rocky, some orbit in the habitable zone, some have atmospheres. The question of whether any of them have life is the question of our generation. If we find even microbial life, even the remnants of ancient microbes in a Martian rock, it will be one of the most profound discoveries in human history. Because it would mean that life isn't a fluke. It would mean the universe is alive. The future of the universe. And the end of everything. The fate of the sun and the earth. Let's talk about endings. In about 1 billion years, the sun will have brightened by about 10% compared to today. That doesn't sound like much, but it'll be enough to kick off a runaway greenhouse effect on Earth. The oceans will start to evaporate. The atmosphere will change. Complex life, as we know, it will become increasingly difficult. In about 3.75 billion years, something spectacular will happen. The Milky Way will collide with our nearest major galactic neighbor, the Andromeda Galaxy. Don't panic, galactic collisions are mostly empty space colliding with empty space. The stars are so far apart that actual stellar collisions are rare. But the gravitational interaction will reshape both galaxies over hundreds of millions of years, ultimately merging into a new elliptical galaxy that astronomers have already named Milkomeda. Our solar system will likely be flung into a new part of the merged galaxy. The night sky will be transformed, filled with new stars, new nebulae, the chaotic beauty of two galaxies becoming one. Then, in about 5 billion years, our sun becomes a red giant, as we discussed. It expands. The inner planets face their fate. Earth, if it hasn't already been stripped of its atmosphere and sterilized, may be engulfed entirely. What was once a living world becomes a silent cinder, or is dispersed entirely into gas. After the red giant phase, the sun becomes a white dwarf, a slowly cooling point of light, dimming over billions of years into darkness. Our solar system, after 10 billion years of activity, will go quiet. But the universe will continue. For a very, very long time. Theories about the end of the universe. Cosmologists have proposed several possible endings for the universe, and they're all appropriately dramatic. The Big Freeze, heat death. This is currently the most scientifically favored scenario. As the universe expands and cools, stars burn out one by one. Black holes swallow what's left. Eventually, even black holes evaporate through Hawking radiation. The universe becomes a cold, dark, nearly empty expanse. A thin gas of particles slowly spreading further and further apart. Nothing happens. Nothing can happen. Every source of usable energy has been exhausted. Physicists call this maximum entropy, a state of perfect thermodynamic equilibrium. The universe isn't destroyed. It just runs down, like a clock that's unwound completely. This would happen on timescales so vast they're almost impossible to express. We're talking numbers like 10 to the power of 100 years, a 1 followed by 100 zeros. For context, the current age of the universe is about 1.4 times 10 to the power of 10 years. We're nowhere near the end. The Big Rip, remember dark energy, that mysterious force accelerating the expansion of the universe? If dark energy grows stronger over time, the expansion could accelerate to the point where it overcomes not just the gravity between galaxies, but between stars, between planets, between molecules, and ultimately between the fundamental particles of atoms. Everything would be torn apart, from the cosmic scale down to the subatomic scale, in a final, all-encompassing catastrophe called the Big Rip. Galaxies are torn apart. Solar systems disintegrate. Planets explode. Even atoms are ripped to pieces. And then there's nothing. How soon could this happen? If dark energy is strong enough, maybe in about 22 billion years. Or maybe never, it depends on the nature of dark energy, which we still don't understand. The Big Crunch, in this scenario, the expansion of the universe eventually stops and reverses. Gravity wins. Everything starts falling back together. Galaxies merge, stars collide, temperatures rise. The universe contracts back to a state of almost unimaginable density and heat. A reverse Big Bang. A singularity. And then, maybe a new Big Bang. Maybe the universe bounces and starts over. This is called the oscillating universe or Big Bounce model. The idea that the universe goes through endless cycles of expansion and contraction, Big Bang to Big Crunch, forever. Most evidence today suggests the expansion is accelerating, not decelerating, making a big crunch seem unlikely. But cosmology has surprised us before. Vacuum decay. This one is my personal favorite for sheer existential horror. Quantum field theory suggests that the universe exists in an energy state called the electroweak vacuum. Physicists aren't entirely sure this is the lowest possible energy state. It might be a metastable state, like a ball balanced on the side of a hill rather than sitting at the bottom. If that's true, somewhere in the universe, a quantum fluctuation could trigger a transition to a lower energy state. This would create a bubble of true vacuum, expanding outward at the speed of light, fundamentally altering the laws of physics as it sweeps through space. Atoms, as we know them, would cease to exist inside that bubble. Chemistry, biology, everything, all instantly incompatible with the new vacuum. And because it expands at the speed of light, you'd have no warning. One moment you exist. The next moment, the bubble has reached you and the laws of physics you're built on simply no longer apply. The good news: physicists think if this were going to happen, it's so improbable that the universe would likely survive far longer than the Big Freeze timeline. The not-so-good news: we can't be completely certain. What remains after everything ends? After the Big Freeze, after the black holes evaporate, after the last particles slowly decay, what's left? In the most distant future imaginable, the answer might be almost nothing. A nearly empty space filled with an extraordinarily thin gas of the most stable particles, electrons and positrons, photons of such low energy they barely register, separated by unimaginable distances, doing nothing, going nowhere. But here's something worth holding on to. The universe, in its current chapter, has created something remarkable: minds. Beings capable of looking back at the cosmos and understanding it. The universe, in a very real sense, became aware of itself through us, and through whatever other forms of consciousness might exist out there, waiting to be found. In the grand sweep of cosmic time, this chapter, the stelliferous era, the age of stars, is vanishingly brief. It lasts roughly 100 trillion years, and we're only about 14 billion years in. We're at the very beginning. And in this beginning, in this tiny sliver of cosmic time, a species on a small rocky planet around an average star figured out how to measure the universe. They discovered the Big Bang. They photographed black holes. They detected gravitational waves, literal ripples in space-time, from events a billion light-years away. They asked where everything came from, and kept asking even when the answers led to more questions. That's us. That's you right now at the end of this journey through the cosmos. The universe doesn't know it exists, but you do, and you spent the last hour thinking about it. That, honestly, is one of the most remarkable things in all of space. We covered a lot of ground today, from the unimaginable size of the universe, to the monsters at the center of galaxies, to the possibility that life is brewing in the hidden oceans of an icy moon just a few 100 million miles away. Space isn't just a backdrop. It's a story, the biggest story there is, and we're characters in it. Small ones, yes, fragile ones, but curious ones. And curiosity, it turns out, can reach very, very far. Thanks for listening. Keep looking up.